Hi everyone, thank you for coming. My name is Shlomi Noach. I'm with the GitHub database infrastructure team. This is a 45-ish minute session about our MySQL high availability setup. So I'm going to just describe how we manage high availability for MySQL. I'm going to illustrate our previous setup and what was wrong with it and why we moved to the new setup and some considerations and limitations and various issues and concerns with high availability. So I'm with the database infrastructure team. I author a bunch of open source projects, Orchestrator, which I'm going to present very shortly here, Ghost for schema migrations, and other projects. I blog at openarc.org. I guess everyone knows what GitHub is. Lots of nice t-shirts. I'm sure you've heard about the Microsoft acquisition. We can take this offline and talk about this later. But basically, we provide Git hosting. We're the largest open source host in the world, which means we are busy and we want to be up and we want to be available naturally. We do use MySQL behind the scenes quite a lot. So your Git repos are in Git, but all the metadata is in MySQL. So all your users, your organizations, your issues, your pull requests, your comments, but actually everything that has to do with Git itself, like every commit, it's in Git, but it's also in MySQL, so that you can click the commit and get to the commit page and show the diff between the old code and the new code, right? Every push that you do, that's MySQL, that goes to MySQL as well. So there's a lot of metadata, obviously, and a lot of traffic. And we want MySQL to be available whenever you push, whenever you commit, because that's something you want to be able to reflect in the website, in the API, etc. So MySQL runs our website, API, authentication, and a bunch of other stuff. Our MySQL setup is not extremely large, so at about 15 terabytes of total data. Not everything is OLTP, but that's the general number. At around 150 production servers, it's not small, it's not huge. I'm sure you can find much larger MySQL setups. But what's important for us is that it is available. That's like really critical. If GitHub is down, like everyone, all the Twitter is down because everyone is tweeting that GitHub is down, right? So we are at the crossroad of a lot of workflows. The entire, like NPMs and Go libraries and CI builds, everything goes through. And if GitHub is down, that's not good. So my team is in charge for the high availability of MySQL itself. So when I talk about MySQL high availability, what do I mean? What does high availability even mean? So we want our servers to be both reachable to writes and to reads. And today I'm going to talk more about the writes. We want them to be available. And in the event of a failure, we want an automated process that kicks in and reliably fails over. So if a master dies, it reliably fails over to a new master. And it doesn't just reliably fail over, it needs to reliably detect the failure and hopefully not fail over for nothing. So we want to avoid false positives. Obviously, we want to avoid false negatives. We want every failover to be justified and every failure to be failed over. We want to be able to cope with complete data center isolation. So there's a bunch of considerations that we want to be able to walk through. And of course, we want the failover to run in a reasonable amount of time. So I'm going to share with you what we've come up to. So again, with high availability, we can talk about availability for writes and availability for reads. All things MySQL, the two are quite distinct because because of the way MySQL works, right? Is everyone familiar with MySQL replication? Like the single master. Let me jump ahead a few slides, right? So a normal MySQL topology looks like this. Like there's a single writer, a single master. You put all the writes onto the master, and then there could be replicas and sub-replicas, and those replicas will typically scale out to serve the read load. Now, the two problems of write availability and read availability are quite different, because write availability is all on that single instance, where read availability is like pick 2 out of 5 and we'll be fine, etc. So this session discusses write availability. And what does write availability even mean? To be able to write to MySQL, the master needs to be up and available, right? And if the master fails, there's 3 things that need to happen for you to feel that MySQL is available again. So the first thing that needs to happen is that you need to be able to detect the failure. That takes time. You need to reliably detect that the master is died and there's a justified cause for failover. And then you need to do the failover, which takes time. And the last and often neglected piece of action that you need to take is to let everyone know that the master is failover. You need to advertise the identity of the new master. And this is often overlooked and is actually, I think, a far greater problem than what people often think it is. Because advertising the identity of a new server means shipping the information to various places, and there are scenarios where maybe some parts of the the destination will not get the message. You could run into split brains. There could be various scenarios which are bad for your health. So we're going to discuss all 3 and see how the 3 interact between themselves. So the first 2, so detection and recovery, these 2 are both handled by orchestrator. Please raise your hand if you're familiar with orchestrator, have heard about this before. Okay, cool. So orchestrator is an open source replication management and failover solution. I began writing orchestrator 4 years ago while I was working at a company called Outbrain, which was happy to release it as open source. I then moved to work for Booking.com and continue to work on that open source project at Booking.com, solving high availability for Booking.com. And then I moved to GitHub, and it's the 3rd company where I continue working on the same open source project. So that's pretty amazing, and I'm really thankful for, yay to open source. And the thing is that it's a solution that monitors your MySQL topologies. It understands replication rules. It understands what MySQL is, what versions are, what kind of replication you can have, and it can fail over masters intelligently, and I'll really discuss very briefly. It was written as a generic product, which is why I was able to take it from one company to the other to the next one, and I encourage you to try and use it. So it's free and available. It's Apache 2 license. It's open source. It's well maintained. It's been maintained today by GitHub. So what orchestrator does is basically 3 things. One thing is that it discovers your topologies. You tell orchestrator, hey, I've got this topology. Here's a server in that topology. And it will go and interrogate the server. Who are you? What kind of version are you running? What's your configuration? Binary logs, binlog format, whatever. Do you have a master? Do you have replicas? And then it will crawl up and down the topology and discover the entire topology. And as your topology changes, orchestrator will adapt and discover the changes to that topology. That's one thing. The other thing is that orchestrator allows refactoring, so that I could move this server from replicating from this node, move it here, change the topology, right? Maybe I want to upgrade this server right now. Let's take these 2, put them over here, upgrade that. Those things are made trivial by orchestrator. The last thing is recovery, crash recovery, which is what we're going to talk about today. So at GitHub, we run orchestrator. We run a variant of orchestrator called orchestrator on raft, which is a deployment setup, which I'll further describe shortly. We run automated failovers. Everything is automated. We will wake up in the middle of the night, but we don't want to do those operations in the middle of the night, should there be a failover. So yeah, we're running it well into production. And that's actually a real obfuscated cluster. We have 3 data centers right now that we're running on. So that's one of our smaller clusters. So like really a 5-minute breakdown into what orchestrator is and what makes it different than other tools. So I'm going to present 2 things. How is orchestrator different in detecting failure, and how is orchestrator different in resolving a failure, right? So failure detection. You have a single master, you have the topology. There are many approaches to deciding whether a master is dead, whether you should kick a failover. And the naive approach, the very naive approach, which I'm glad to say more and more tooling today are walking away from that approach. The naive approach says, okay, let's set up a Nagios check, right? And that Nagios check will do ping the host, ping the port 3306, maybe even issue a select one, right, to see that the master is alive. Does that make sense? Yeah. Okay, so you issue a select one on the master. It says 1. Does that mean the master is alive? Are you happy? Basically yes, because it responded. Maybe you could select something from a table. You'll be very happy. What if you don't get a response? What do you do then? Is the master dead? You do a select one, you get an error. Is the master dead? Yes or no? Maybe? So maybe. How can you change your maybe opinion into something more substantial? Check again. That's what the naive approach does. It says, okay, well, maybe there was a network glitch, a hiccup, right? Maybe the monitoring server was isolated. It's something, let's try again. So let's wait 3 seconds, try again. Error. Is the master dead? Yes or no? Are you sure the master is dead now? Or is it still maybe? Most people will say maybe, because flipping over a master when you don't need to flip over a master is kind of a drastic move. So let's wait another 3 more seconds and check again. And then maybe, but maybe smaller. And then, so there's some magic numbers here. What's the number of how many seconds do you wait between every 2 checks, and how many checks are you going to make, right? And say you said 3 and 4, so you end up with 12 seconds wait or something like that. If the master was really dead, you just wasted 12 seconds because you weren't sure. And you're still not really sure at the end of this process. You've just reduced your maybiness, right? your uncertainty. So orchestrator takes a very different approach. Orchestrator says, well, the master is not the only piece in this puzzle. There's a master and there's replicas, right? That's the big deal. We have replicas. And the replicas, by nature of MySQL replication, they also know what the state of the master is. Or rather, they know whether they're able to connect the master and get changes or not. So what orchestrator does is say, I'm not going to just ask the master, I'm going to also consult the replicas. Because I'm orchestrator and I know what the topology is. I know what it looked like 5 seconds ago. So I can expect to talk to these 3 replicas and ask them, hey, I checked the master and I can't see it. What do you think? And if the 3 replicas say, yeah, replication works, we're happy, then orchestrator says, yeah, okay, so who am I to decide, they say they're happy, it's me, the problem is with me. But if everyone says, oh yeah, the master is dead, I can't reach it, I have IO error or whatever, then orchestrator says, well, now I have it's me and that replica and that one, everyone agrees that the master is dead. Now listen to this, it doesn't even matter whether the master is dead or not. It doesn't even matter. At this time, the uncertainty is irrelevant because all the replicas are not replicating. They all say we're not replicating. So who cares if the master is dead or not? Replication doesn't work anyway. Like everything is broken. So it's quite justified to fail over in this scenario. So we call this the holistic approach. I don't have nines to tell you, like 5 nines, 6 nines. We don't have gazillions of failovers, right? But this is very, very reliable to the extent that in the past 2 years, since we implemented orchestrator at GitHub, 2.5 years, we never had a single false positive. We never had a failure when we shouldn't, like when the master was still alive. Every failover we had was justified. So it's pretty trustworthy. Another thing about orchestrator is how it chooses to promote a replica. The naive approach says, okay, the master is dead. There's 3 replicas. Let's promote the one that is most up to date, right? That's what makes sense to everyone, but that's actually an anti-pattern because the most up to date might actually be the very one that you don't want to promote. Servers have different configurations, different versions. You can't promote a 5.7 and expect that it will replicate into a 5.6. That's a constraint. You can't promote a server which doesn't have binary logs. So orchestrator understands all the replication rules and it understands what it would mean if I promoted that server or that server, and it will try to make the best out of the situation, much like what a human being would do, hopefully not in 2 a.m., but after some coffee. What a human being would decide to say, okay, if I promote that, I'm going to lose all those servers because they can't replicate from that server. But if I promote that, I lose only one. All right, my choice is clear. That's the kind of reasoning that orchestrator makes. Moving on, so that part is pretty covered. I mean, there's always much to improve, and we're improving, and I'll talk a little bit later about something with orchestrator, but basically we have detection, and we have failover, and that's been in place for over 2 years now at GitHub, so it's pretty much okay. Now, I want to discuss how the master discovery part was implemented at GitHub until fairly recently, and what kind of problems we saw with that. So until recently, the way we would advertise the identity of the master to the clients was based on VIP and DNS. That is, clients, like an application, like a Ruby application, would not know the true identity of the master, but it would know it would have a VIP, a name, which would resolve to a virtual IP. And the master would grab that virtual IP so that if the client connects to the virtual IP, well, the master answers at the other end of the phone, right? And basically, at the time of failover, what we would do is to move the VIP. Say we would want to promote this server. We would move the VIP from here. Orchestrator would promote that server, and then we would move the VIP from that host to that host. Does that make sense? All right. So there's various ways to implement VIPs, but they all kind of have similar problems, more or less. I'm not a network expert, so I'm sure there are people here who would know much more about VIPs than I. But basically, we would have these problems. So the first thing is that VIP is a cooperative. VIP assignment is a cooperative operation, right? To get a VIP, you send an ARP request to your router, to your switch, get the VIP. You can't just burst in. A second server can't just burst in and say, oh, hey, I want that VIP. No, that VIP is already assigned to the first server. You can't get it now. We must first deassign it from the first server. Now, the failover script or the failover flow that we had, so orchestrator would promote a new server, and then it would say, OK, now we need to move the VIP from one server to another. Well, old master, can you please give up your VIP? All right? Is that a fair request? So and so. I mean, there's a problem on that server, right? There's a reason we failed over. That server is already in trouble. Maybe the trouble is on MySQL, and you're able to, I don't know, remote SSH or remote exec something and say, give up the VIP. But maybe not, because there's there's likelihood that that server is having a bad day, and maybe you won't even be able to ask it to remove the VIP. At which case, you may not be able to reassign the VIP to the newly promoted server. Now, to clarify, this actually never happened for us at GitHub, but did happen to me at a previous job multiple times. I've seen this happen multiple times, and I've always felt like this is like a dark corner that I don't like. And moreover, like, I really want to promote that server, but first I need to go into the old server to ask it to remove the VIP. It's kind of, I'm going to need to wait for the approval of someone before I go to the next server. This is stalling my failover, right? I'm going to need to wait. Why? Why should I waste so much time on the old server when I don't want the old server? I want to throw it into the garbage. I want to promote the new server. There's other constraints, like some of our VIPs were bound by physical location. There's, like I said, there's different ways to implement VIPs, but some of our VIPs were constrained by a local switch, which meant I couldn't just promote any server I wanted, but only servers which were connected to the same switch. And the next thing was cross-DC, because cross-DC didn't work well. And so to change a VIP cross-DC wouldn't work. What we would do instead is change a DNS entry, where in the other DC, someone would assume the same VIP, and that takes a lot of time because clients cache the DNS entries. There's a TTL of like 60 seconds, maybe 5 minutes, or what have you. It's certainly not 1 or 2 seconds for caching DNS entries. And so a cross-DC failover would take a lot more time. And then there's also the question of how do you update all DNS servers in different databases with the information that the DNS entry has changed. That adds more complexity and more friction to the process. So, and this worked. We had successful failovers that you were not aware of because they worked, but we didn't feel comfortable with them. And so we changed this. So what's the new story? Let me just check the time. Perfect. I'm saying perfect, but I don't remember what time I began talking. So the new story is based on orchestrator, Consul, and proxy. That's actually a paradigm which is growing in today's world. If you look into like Kubernetes, that's the same paradigm. What does Kubernetes have? Kubernetes has load balancers on front, right? It has a service discovery, which is etcd by default for Kubernetes. And then it has an orchestration layer that knows, given that some attributes changed in etcd, let's change the behavior of the load balancer. So it's a paradigm that is growing, and we are using a similar paradigm. So we use HAProxy, Anycast IPs, Consul, orchestrator, and semi-synchronous replication to achieve something that is, we believe, far better than our previous iteration. So here's a nice fish, something. I'm going to go back to this drawing later on, but basically, let me just, like, different colors are different data centers. This is an application. These are load balancers, and there's a lot of mess in between. I'll get back to that slide, I promise, in a few slides. It's going to come back, and then we'll explain it. So the story gets rid of VIPs and DNSs and introduces new components. It actually introduces more components than before. But even though it adds more components, it adds them in what I strongly believe is a safer and more reliable way, because it promotes a decoupled strategy and a clear sense of ownership into each and every part. So there's more components, but they're less dependent on each other, and they can each operate like on and focus on what they do best. And they are each highly available and trusted. So we feel very comfortable with that setup. So what are the components? First is GLB. GLB is GitHub's load balancer, GitHub load balancer. we actually run HAProxy behind the scenes. And the GLB is like a coordinator wrapper around an array of HAProxy servers. So making HAProxy highly available, and then some many, many more added features. But for our discussion, let's just assume, simplify things, and GLB is like a set of HAProxy servers, okay? Making them highly available. Is that okay? Cool. The next thing is Consul. Raise your hand if you're familiar with Consul. Okay, cool. So for those who don't know, Consul is an open source service discovery solution by HashiCorp. It's widely used today. I think it's about 4 years old. I began writing orchestrator at around the same time the first 0.0, Consul release came to be. So Consul runs service discovery, health checks, DNS. It is a highly available setup, so you would have like 3 or 5 Consul servers talking to each other. But for our purposes, I'm only using a small fraction of Consul, which is, I'm using it as a distributed, highly available key value store. So Consul is just a service that allows you to say key value. The key will be master of cluster number 1, and the value would be the host name or the IP and port for that master. Consul template is a sidekick to Consul. Consul template is a service that listens to Consul on one side and generates usually a text file on the other side. So Consul template can listen on a change to a key value in Consul, right? And as an input, you would give Consul template some file with special marker tags, right? And Consul template will replace those magic tags with the value from key value. Does that make sense? So it's a template engine that listens on Consul. Now, what Consul template is going to do for us is to generate HAProxy's config file based on the key value information in Consul. All right? And then it also reloads. So you can tell Consul template, anytime you made a change, run something. So please reload HAProxy to reflect those changes. We run orchestrator on raft. Orchestrator is a service that can itself run in a raft cluster. We run orchestrator on raft cross DC. So we have an orchestrator, one or more orchestrator representatives in each of our data centers, and they all talk to each other. Each orchestrator node probes and understands the topologies, but only one of them is running failover, and they do that by getting consensus. And that is using actually the same, the HashiCorp raft library, the same raft mechanism driving Consul. And that, as I'll describe shortly, helps us mitigate DC partitioning. So yeah, we added some stuff to the HashiCorp raft library, which make it more comfortable for us to run it. So let's just explain this story, okay? So we run HAProxy. Each of these is a different data center, and in each of these, we actually have like 5 or 6 or 10 or 20 HAProxy servers, which are highly available. But let's say it's just a HAProxy server. Everyone familiar with HAProxy to some extent? Okay, so HAProxy has a config file, and the config file says which pools do you have, and in each pool, which servers do you have in that pool, right? Usually, we use like HAProxy for read load. We would say, these are all the replicas in MySQL, so you can send queries to any one of those, like round robin, load balance them. But here, we have a pool for each master. There's a pool for the first cluster master. Hey, HAProxy people, great work. There's a pool for the second cluster. There's a pool for the third cluster. And each pool has exactly one backend server, which is the master, right? We need to have exactly one backend server for the master of each topology. And just to avoid confusion, although I have 3 different clusters here, they're spread all over the DCs. Don't confuse. It's not like clustering one DC, clustering second, clustering third. This master could be anywhere. This master could be anywhere. This master could be anywhere. So we would have a config file that says the master for that cluster is this server. The master for that cluster is this server. The master for that cluster is this server. Is that okay so far? The clients, the applications, would only know the IP. They would use Anycast. Anycast IP resolves to different host names based on where you are located physically, which basically means all the apps are set to work with the same IP for the master, but that IP actually resolves to HAProxy. And HAProxy or GLB will relay your request to the appropriate master based on the single backend server it has in the pool. And so the app would connect to HAProxy. That's all it knows. It knows nothing about the master. It knows nothing about the IP of the master. There's no VIP. It doesn't know what data center the master is in. The app only talks to a local HAProxy server. And that HAProxy server says, yeah, OK, your IP maps to this pool. Let's call it pool number 1. And in pool number 1, there is a single backend server. I don't know what that server is. They tell me it's a master, but I don't really care. I don't know about that. I'm going to just route your queries to that server, which thankfully happens to be the master. So far, so good? That's on a good day. On a bad day, master fails. So when master fails, the following happens. Orchestrator observes the topologies and knows that master has failed. Orchestrator will fix the topology and promote a new master, right? So far, no one else is aware of what's going on, except the applications are, of course, freaking out. So once Orchestrator has promoted a new master, it goes to Consul and says, you know, the master for cluster number 3 is now that server instead of that server. And that's all Orchestrator has to do. It doesn't need to talk to the apps. It doesn't need to change VIPs or DNS or anything else. It updates a key value store in Consul. It's a simple operation. Incidentally, every single node in Orchestrator does the same, so you could actually have different local Consul setups, and it will still be able to spread the information reliably across DCs. So all consoles in all DCs, if you have such, will have the same change. So the key value has changed. What does Consul do with that? Absolutely nothing. Consul is just a store. It just makes sure that the key has the value. But Consul template is running on each of these boxes, and Consul templates keeps on listening to consoles and notices, oh, the value for that key has changed. My template file says you should put that value over here. So I'm going to copy and paste the new value onto the template file. Oh, the config file has just changed. The checksum for the config file has changed. I'm going to reload HAProxy. HAProxy reloads, and voila, it has a new identity for a backup server in its cluster 3 pool. And voila, the applications don't need to do anything except stop freaking out, start communicating again. Any ongoing writes they will have to, they will send to HAProxy will be redirected to the new master. Is that okay so far? Good. Whoop, that's not me. Screensaver. All right. In the VIP story, we had another thing that I forgot to mention. Even if VIP moves as expected, and you've wasted the time to remove the VIP from here and assign it to here, works. OK, fine. The fact that you've moved the VIP from one server to another does not necessarily mean anything to the existing connections. So existing connections on the old master will not necessarily die when you move the VIP from that master to the new master. And you could end up with a split brain in case the old master suddenly is back alive, is happy again. How am I with the time? Does anyone know? 10 minutes? 5. Okay, that's good. We're towards the end. And so you could end up with applications talking to either the old master or the new master, which is a very bad scenario. Here, applications cannot possibly talk to both because the proxy will direct all traffic either to this one or to that one. And we've configured a hard timeout, a hard stop. What's the name of the variable? Hard stop after in HAProxy to say, since we changed the identity of the server in the pool, I'm going to rigorously kill the connections to the old server, to the one that is not in the pool anymore. So even if applications were somehow still thinking they want to talk to the old master, the proxy would kill those connections within some time, a second or two. It takes some time, right? It's not hermetic. It's not 100% guaranteed, not at all. This is not a completely bulletproof solution, but reasonably shortly after, you could say, okay, during that time, I don't know, there was a mess, but now everything's okay. So there's trade-off here, right? I'm not trying to sell you that this is, well, a perfect solution, but it's a good one. All right, so orchestrator owns the recovery and updates console. Console templates takes the changes from console to GLB. GLB reroutes the connections and kills the old connections. The applications connect to GLB, and yeah, that's pretty much it. So replace console with etcd, replace console template with something else. The components are independent of each other, right? Orchestrator doesn't care about HAProxy, and the clients don't care about Orchestrator. No one talks to anyone. Like, this is a very decoupled design. Moreover, there's other stuff you want to do when you fail over. We run PT heartbeat. You want to stop PT heartbeat on the old master and start it on the new master, right? Are you familiar? We just decided to run it everywhere. Why stop and start? It wastes time during failover to tell that server start PT heartbeat, to tell that server stop PT heartbeat. We just run it everywhere, and where the server is read-only, it just goes to sleep. So when the new master is promoted, PT heartbeat is already there, already running, and magically working. A word about semi-synchronous replication. We are running semi-synchronous replication to hopefully avoid data loss. We set it with a 500 millisecond timeout, which means most of the time, or in most cases, we really expect failovers to be lossless. When the master dies, some replica has all the information that it got from the master. If you're unfamiliar with semi-synchronous, it's a little bit over the top to explain it here. But basically, it helps us in achieving lossless failovers most of the time. But we don't guarantee it, because to guarantee a complete lossless failover is a very highly expensive guarantee, right? You need to lose a lot to guarantee that, and it's okay if you need to. We decided we don't necessarily need to, but most of the time we do expect lossless replication. And there's an optimization part. We can take that offline. It's a little bit more complicated. It helps us improve and reduce the overall outage time by making the right replica be the ideal candidate for promotion. I can elaborate later on. It's a longer story. But basically, using semi-synchronous replication along with an orchestrator optimization helps us reduce 8 to 9 seconds of failover time. So what are the results? Most of the time, we expect like at around 13 seconds or just a little bit less. Total outage time. Total outage time, I remind you, from the moment the master is actually stopped responding, right, crashed, died, and this includes discovery time, failover time, and shipping the information, right, and advertisement time. from the time the master died to the time where applications are able to write to the new master. That's the total outage time. It stands at 13 seconds. Like, that's the most common case. We do have lesser cases where we go down to or up to 25 seconds total outage time. We prefer those numbers, but we can get those on rarer occasions. Now, having lower numbers is like not a problem. I can have like 1 second total outage time if I just change some VIP, you know, just because I wanted to. But having that amount of time for reliable failovers, that is a better achievement, considering you don't get false positives. Hopefully you don't get false negatives. So it's a good number to reach when the failover is reliable. Because having like, I could have 20 unnecessary failovers per day that would take 5 seconds to failover, but that's not as good. There are disadvantages to this approach as well. It's not perfect. Our masters, so our clients don't know who the master is because they go through proxy. Our masters don't know who the clients are. All they see is connections coming from the proxy, not from the apps themselves, so it loses some visibility. We are working on a shoot the other node solution. What happens if there's a DC isolation? We didn't elaborate, but orchestrator solves DC network isolation by ensuring that a master from the non-isolated server is promoted. That I didn't try it. I didn't try pulling the plug off an entire DC recently. I'm not sure they're going to let me. I'll see. Maybe I'll sneak in and pull the plug. But there's another problem. What happens within the isolated DC where applications might think they are eligible to continue writing to the master? And we're working on that as well. We have testing for that, but let's take this offline. So what we're working right now is Stoneth. We're trying to close more gaps. There are many gaps in this story. This is a distributed system with many components. You cannot hermetically close it without paying the ultimate price, which is like infinite development time and infinite money and etc. So we do take like some compromise. We try to lose more loopholes, so there's work on that. Yeah, there's thought about like making this like an appliance which you could sell or not sell, like giveaways, you know, as a wrapped up solution. That's it for me. I'm happy to take questions. A couple questions. We don't have much time. Yes, Alex?
Well, I have 7 questions.
Yes.
But I don't have time for that. I have 6 technical questions and 1 non-technical question. So which one do you prefer?
Choose.
Okay, non-technical question.
Yes.
What do you think about Microsoft acquisition?
Let's take it offline. It's a lot to talk about.
1 technical question.
Yes.
You were talking about the semi-synchronous application,
yes.
right? So I assume that there are not that many writes via reads. So what is the percentage of that? And a second related question to that is, have you tried like synchronous or virtual synchronous application?
Okay. So to answer the second question, we didn't try Galera, we didn't try PXC, we didn't try InnoDB cluster. It's something like, you know, each of us people in this room have this pile of technologies that is sitting on our desk that we need to investigate. So yeah, it's somewhere in the to-do list for sometime in the future. With regard to your question about semi-sync, yes, of course, we do have more reads than writes. The ratio is like, I don't know if I can even say what the ratio is, not because I'm not allowed to say. It's like an enormous ratio, right? Many more reads than writes. Yeah, depending on the cluster, we could have like hundreds of writes per second or maybe thousands, not more than that. We don't have like tens of thousands of writes per master per second or something. Never. What we're looking into sharding. The story is that we're looking into Vitess right now for sharding because we do get sometimes masters being overwhelmed with writes, so we're looking to solve that by reducing writes by sharding. More question? More technical question? Anyone else? Thank you so much.